In our last video, we talked about concentrations and molarity, and today we're going to take that quantity and calculate dilutions and also how to use solutions in reactions. So the first thing we have is what is a dilution. So you've probably all done this before, whether it's with orange juice or with tomato soup. You add a can of concentrate and then you add some set amount of water or milk or whatever that you're diluting it with. So for example, here we have 1 can of orange juice concentrate, which we pour into the pitcher, and then you add 3 cans of water. So that's one example, real-world example of a dilution. But a dilution really is just the addition of a solvent, usually water, to increase the volume, but you don't change the amount of solute. So when we, before and after the dilution, so we start with 1 can of orange juice concentrate, and at the end we have a much larger volume, but we still only have 1 can of orange juice concentrate, right? So the amount of orange in the pitcher on the left is equal to the amount of the amount of orange in the pitcher on the right. So we can use, to calculate the new concentration, we can use the equation C1V1 equals C2V2, where C is the concentration and V is the volume. So these two quantities are inversely proportional. The larger you make the volume, the lower the concentration is going to be. And so this equation will get us that information. One thing to note, I learned this equation as M1V1 equals M2V2, M being molarity, and that's the quantity that we're going to be putting in there. So I will use them interchangeably without thinking, but the one in your textbook is C1V1 equals C2V2. Okay, so let's do an example. So what is the molarity of a solution that is prepared when 75 milliliters of a 4 molar KCl solution is diluted to a volume of 500 milliliters? Okay, so we want to use our new equation that we just learned, C1V1 equals C2V2. And here we know that our initial volume and concentration are 75 and 4. So those are the things we're starting with. So we can put in 75 milliliters as our volume and 4.00 molar as our concentration. And that's going to equal our new concentration, which is what we're trying to find. We're looking for the molarity, times the new volume. So we diluted our solution to 500 milliliters, and so that will be our second volume. One thing to note, in your molarity calculations, you always need to have the volume in liters. In these calculations, the units of the volume just need to be the same. So in this case, in this problem, we have milliliters here and milliliters here, so we don't need to convert it to liters because that conversion would just cancel out on both sides of the equation. Okay, so now we just do algebra to solve for C2, and we find that C2 is equal to 0.600 molar. Okay, so now we can expand and use these calculations in reactions. So this example is zinc reacts with HCl to produce hydrogen gas, which is H2, and zinc chloride, ZnCl2. How many liters of a 1.5 molar HCl solution completely react with 5.32 grams of zinc? All right, and to make the plan a little bit more clear, I'm going to rewrite the balanced equation. So we have zinc plus 2HCl plus H2 plus ZnCl2. All right, and what we're trying to find is the liters of HCl. So that's what we're looking for. And what we're given is 5.32 grams of zinc. So we want to go from zinc to HCl, and we know that no matter which two things we're converting between in our balance equation, the only way to get from one kind of thing to another is to go through moles. So we know how to get from 5.32 grams of zinc to moles of zinc, and then we can get from moles of zinc to moles of HCl using our balanced equation, all right, and our ratio there is 1 to 2, and then we can get from moles of HCl to liters using the concentration. So our problem tells us that we have a 1.50 molar solution. And remember, molar is just moles per liter. So we can use that as a conversion factor. All right, so now that we have our plan, we know that 5.32 is the number we need to start with. So we have 5.32 grams of zinc. and our molar mass is 65.41, so that will go on the bottom, so the grams cancel, and we'll have 1 mole of zinc on the top. All right, in our equation, the coefficient of zinc is 1, so that's going to go on the bottom, and the coefficient of HCl is 2, so that will go on the top. All right, and then we need to use the concentration that we're given in the problem, so we know that 1.50 moles of HCl is what we would find in 1 liter of that solution. Okay, so now we just multiply all of this out, and we end up with 0.108 liters of our HCl solution. Okay, so what we've done here is now expand this web, which I alluded to a little bit in the last video. And what we did in this problem was we went from grams of one thing to liters of solution of another thing. Okay, but we could do that with any quantities. We could go from liters of one solution to liters of a different solution. We could go from liters of a solution to liters of a gas. We could go from liters of a gas to grams of a solid. Any of these possibilities are fine, but we always go from moles to moles using that mole-mole factor in our balanced equation. Okay, so let's do one more example of this. So acid rain results from the reaction of nitrogen dioxide with water in the air. Okay, at STP, how many liters of NO2 gas are required to produce 0.275 liters of a 0.400 molar HNO3 solution? Okay, so again, I'm going to write out my balanced equation because I find that to be the easiest way to organize my problem. So we have 3 NO2 plus H2O goes to 2 HNO3 plus NO. And the problem tells us that we have 0.275 liters of HNO3 solution, so I'm going to write that under there. And we're trying to find liters of NO2. Okay, so we can get from liters of the HNO3 solution using the molarity, which is right here in our problem. So 0.4 would get us that number of moles. And we can get from moles of nitric acid to moles of NO2 using the ratios in our balanced equation. And then we can get from moles to liters of gas using the standard molar volume. So if you remember from the last chapter, at STP, which is what we are in this problem, 1 mole of gas is 22.4 liters of gas. Okay, so now we have our plan. We have all the numbers we need, so we just need to set up our problem. So we have 0.275 liters times 0.4 moles in 1 liter, because that's our concentration of our nitric acid solution. Okay, and then we want moles of nitric acid on the bottom, so there's we'll use 2 because that's the coefficient in our equation, and then on the top we'll have 3 moles of NO2 because that's what we're trying to get to. And then, as I just said, 1 mole of NO2 at STP is 22.4 liters of NO2. So we multiply all of those things out, and we get 3.70 liters of NO2. All right, so we're going to do lots of problems like these in class and on Mastering Chemistry, so you can get really good at them. But really, the key is planning what you have and what you need to find, and then finding all the values that you need to get from one place to the other. But it's sometimes challenging in these problems because there'll be multiple numbers given to figure out what goes out in front, which is why it's so important to make the plan before you start trying to do calculations.